Hello students, welcome back. Today myself Manjunath Guru, I'll be teaching a topic on very interesting, that is design on knuckle joint design, which is also called as pin joint. Okay, before I start, I always tell you to like my channel, subscribe to my channel, comment if you have any doubt, and also share to the maximum. Okay then, without any further resume, let's begin. Knuckle joint or pin joint. This is the diagram of the knuckle joint. This is the front view and this is the top view. Okay students? Yeah. Now we'll see the various, like what is knuckle joint. Let us understand that before we get into it. Knuckle or pin joint, this joint is used to connect the rods when a small amount of flexibility or angular movement is necessary. One end of the rod is pulled in the form of a fork having uh, both arms of the fork. It has double eye end or fork end. The end of the other rod is forged, forming a single eye end. Okay, that is the theory part. It is not that much important, students. It is placed. You should only know what is important. I'll just tell you. It is placed. It is placed with a double eye end and a cylindrical pin inserted through a hole, as shown in the figure 9.3. It is then kept in a position by means of collar and taper pin. The two rods are quite free to rotate on the cylindrical pin. This joint commonly used in the reciprocating motion is to convert into rotary motion or vice versa. Next, these are very important students. Now, design of knuckle joint. Consider a knuckle joint connecting two rods subjected to tensile load as shown in the figure. F is the load in Newton, D is the dia of the rod in mm, D2 is the dia of the pin. So here with respect to the figure we have, okay, everything is clear. So this is the force F and D is the diameter of the rod. Then we have our diameter of the pin is D2, diameter of the pin is D2, and we also have a diameter of the pin head is D3 and diameter outer dia of the eye is D4. Okay, 4 D4 and D3. Okay, then we also have thickness of the single eye in mm and thickness of the fork in mm, that is B and E. Fork is A, okay, fork is with respect to A, this one, this and these two forks, and B, we have B as the thickness of the single eye. Thickness of the pin head is H, thickness of the pin head is H, and then thickness of the single eye means this is the eye, okay, single eye end. These things are also available in the data handbook. That's fine, not an issue, student. Now friends, so we have sigma x is the permissible tensile stress in Newton per mm square. This is tensile is sigma T, sigma C is your crushing, tau is your shear stress. Everything is expressed in Newton per mm square. The dimension of the knuckle joint may be obtained considering various modes of failure discussed below. Tensile stress sigma T is equal to, this is actually sigma T is force by area. So area equals circular cross section. So area will be pi d square by 4. That is also available in the data handbook, given in the equation. It will be discussed in the problem, then you will now understand. This is also shear stress is denoted by tau equals, it's also same, but it will be in by 2. So you should understand twice. So this will be 2f by pi d2 square. Then these things are also available in the data handbook. Compressive stress in the eye due to bearing pressure sigma c. Compressing is sigma c is F by dB, force by area in terms of d2 and b. Then shear stress in the eye tau equals F force by d2 minus d4 minus d2 into b. Then tensile stress in the net area of the eye equals sigma t. These equations are readily available in the data handbook. F upon the same equation. Only thing is you will be computing the tensile stress here, and when it comes to shear stress in the fork end, it will be F upon 2a into d4 minus d2. These empirical relation formulas are not required to be derived, but you need to know which is readily available in the data handbook. These two equations are also similar, but here it is sigma t, that is tensile stress in the net area of the fork end. Compressive stress in the fork due to the bearing pressure sigma c equals F upon 2 times d2. This is similar to this. Then most of the equations look similar. All these things are actually readily available in the data handbook, students. You can just go through that. Maximum bending stress in the pin sigma b equals 4fb upon pi d2 cube. The head diameter of the pin d3 equals 1.5 b d, and thickness of the pin head is, that is h equals 0.5 d. Various relations. And okay students, now yeah, that is with respect to that. Then we also have, if there are two formulae to determine one unknown dimension, use one formula to find the unknown and the other to check the induced stress. These things will be discussed with the problem, student. So let us consider a problem. Now here is the problem. Here goes. Design a knuckle joint to connect two mild steel rods to sustain axial pull of 150 Newton. So what we have, so axial pull is 150 kilonewton, and pin and the rods are made up of the same material. Assume the working stress in the material are 80 megapascals in tension, 40 megapascals in shear, and 120 megapascals in crushing. So here data given is load equals 150 kilonewton, that should be expressed in Newton, 150 into 10 power 3 Newton. Tensile stress is sigma t equals 80 megapascal, 81 MPa equals 1 Newton per mm square. So this will be, always remember students, stress is expressed in Newton per mm square and load is expressed in Newton, and dimensions is always taken in mm when it comes to design or strength of materials also. Shear stress is corresponding is 40 megapascals, so 40 Newton per mm square, and crushing is 120 sigma c Newton per mm square. Now as usual with the above parameters, I have used the same empirical equations. So we have tensile stress in the rod sigma t equals 4f upon pi d square, which is equation number 17.46. This is actually given here, students, this equation. So all these are used simultaneously, like one after the other with the equation number. You can go through this. So sigma t here it is given as 80, and 4 into f, we are just substituting f is 150 into 10 power 3 Newton, then pi into d square. D is the unknown thing. How do we solve? I'll just show you with the calculator, students. So just take this calculator. You can use fx 100 ms, better use fx 991 ms. So here you can see the calculator, so better use the calculator, students. This okay, so just input here, write 80, then alpha press equal to, then okay, so here wait, let me repeat that, student. So what you have to do, first press 80, then alpha equal to, okay, you can observe that what I am pressing here, then press this option, then go for 4 into 150 into 10 power 3, so that will be 10 power 3 upon, press the down, so that will be upon shift pi into, so that will be alpha x square and press shift calc. Press shift calc, you will get solve for x, then press equal to. Then on solving, it will directly give you the answer as 48.59. So 48.59. So is that clear, students? 48 point, actually yes, so it is 48.86 mm. So we have, which is rounded as 50 mm. Similarly, we'll go with shear stress in the knuckle joint pin, which is given by equation 17.53. Tau equals 2f upon pi d2 square. So here we have tau is 40. Remember, students, it is MPa, so we are just using Newton per mm square. So that is 40 Newton per mm square equals 2 into f is again 150 to 10 power 3 by pi into d2 square. You need not use the calculator here. Okay, for timing I'll explain the calculator used again so that you people are familiar with this. I'll just click on this, like on, then I'll just try to input again 40. So this one will be, one second, yeah, I'll just tell them from the first. Okay, so what you have to do, you have to just input 40. Just observe here, students, what I'm doing. So then alpha calc, then this, then you'll have 2 into 150 into 10 power 3, then down, then this will be shift. Okay, this will be into 10 power 3, so into alpha x. So again, you cannot write d2 square and also alpha x square, then shift calc once and solve for x, it will give, then just press equal to, you get 48.86. that's how you find 48.86, which is actually equal to 50 mm. Actually, when you compare this with the, you are, to your surprise, it is actually most of the answers will be same. Here it is 80 by 4. 80 by 4 will be actually equal to the same 40 by 2. Is it, students? So the same equation, but equation numbers are different here. 17.53. Similarly, there is the diameter of the pin D2 equals here diameter of the rod D. Now coming to the third, compressive stress in the eye to the bearing pressure of the pin sigma C equals F by D2 into B. This is sigma C is given as 120. Corresponding thing only you have to take, student. So 120, crushing stress is 120 equals F upon F is 150 into 10 power 3 by D2 we found just now is 50 into B. Now this inputting this B, actually you can also do this if you're not familiar with the calculator. You can just do the cross multiplication. It is lengthy, it will take time, so I have just done with the calculator so that it will reduce your time. You can write this 120 as 120 by 1. I'll tell you how you can do manually. 120 into, just go for cross multiplication, 120 into 50 into B will be equal to 1 into 150 into 10 power 3. Then we have B as 150 into 10 power 3 upon 120 into 50. That will be, yeah, you can just say, okay, press this and directly go for 150 into 10 power 3, then this one is 120 into and 50, so that will be 25. So that's, you can do it like that also, but I don't feel that is comfortable like this. I can just input in this, and I feel finding, let the calculator do the working. So this is how it is, B equal to 25. So how the calculator does the working also I'll show again. This is the simple B equals 25 with the actual method, then you'll get 25 mm. Now my convenient method, which is my favorite also, just as usual, okay, press that delete and go with this also as on, and then just say okay. So what you have to do, you have to just give the equation as 120. So this will be 120, then alpha calc equals press this and 150 into, okay, you can also press this into 10 power and just say 3 again. Don't press, instead of this 10 you can also go with that, and down, and this will be 50 into, and I can do x, then shift calc and this equal to, so it is 25. As simple as that. Whichever you find it easy, you can go with that, students. I'm just telling you. Now shear stress in the eye, tau equals F upon d4 minus d2 into b. That is equation number 17.48. So here d4 only we have to find, d2 we just now found it is 50, and above only we found db as 25, so d4. So observe this, if you go for that cross multiplication method, it's so lengthy, but when I use the calculator, my beautiful calculator, I call it beautiful because it gives me the textbook answer, students. So that's why. So see how I'll input that. Just press this, observe it, then I'll use the brackets, and press, then here you go. D2, D4 will be, will not do anything. Observe that if you just cross multiply, and so it's lower, so lengthy, shift that, shift here, and this is simple. D4 is 200 mm. That is the outside eye of the pin on solving. Next, check for the tensile stress in the net area of the eye. So sigma t equals F upon d4. It's the same equation, F upon d4 minus d2 into b, but here you are checking for your tensile stress. So if I just input this, the same equation, d4 here is 200, we directly get it as 40, which is our sigma. Remaining all the equations are similar. This is 200, this is 50, and 25. Just input, you will get 40, and we are checking the tensile stress. Here it is 80, it is less, so it is safe. We'll just say it is safe. If it is more than this, then it is unsafe. Then you have to go for redesign. That is what is meant by design. Shear stress in the fork end, that is also given by the same equation, but here it's only checking with shear stress. Tau equals F upon 2a into d4 minus d4 minus d2. This equation, this is a, so this will be 17.50. so this will be a is shear stress is 40 and 150 into 10 power 3, and this is 2 into a. You are solving 200 minus 50, d4 we used the previous one. The same thing I'll just tell again, students. So you can also go with calc, yes, okay. So you can just say here, so 40, observe here, students, what where I'm inputting, equals, and this will be 150, then this is, okay, this will be, okay, calc and equal to, will get directly as 12.5 is 12.5 mm, students. Now check for tensile stress in fork end. F equals the same equation we are using, okay, but only it is tensile. So it will be, if you just input all the previous above equation, as usual you will get the same, which is 40, okay. So that will be less than 80 Newton per mm square, which is also safe. And we have bearing pressure, the sigma c equals F upon 2 by d2 into a. This is equation number 17.52. so if F is 150 into 10 power 3, d2 is 50, and a is 12.5. if you just calculate that, this will be 150 for 3 upon 2 into 50 to 12.5. That will be 120. So which is equal or less than, that is we can consider. So we will say it is safe. Okay. And the last sheet, check for bending stress, sigma b equals F4 into F into b. This is, okay, a pi d2 cube. This I have used the data handbook link here. all these are, you can observe which equation, go to the, you should know how to use that data handbook, go to the index sheet, search for knuckle joint, then all the relevant equation, any beat, any version or edition, you can just check all these equations are readily available there. So this is, I'll just write down 17.55, this equation number I missed, 17.55. Okay, if I just input this, this will be 4 into 115 10 power 3 into B is 25. We just now found B, the previous one B, then only we found A, isn't it, students? So B, A was 12.5, so 25, and this will be pi into d2 cube, that is actually, just click on that, 4 into, see students, our calculator is making our work so easy, into 25 upon pi into 50, so 38.197, which is less than 80. 80 is actually given in the question, that is your sigma B, 80, or tensile stress. Okay, next, the last two bits, head dia D3 equals 1.5 D, which is 1.5 into 50, that will be 1.5 into 50 equals 75, and similarly we have head thickness of the pin H equal to 0.5 of D, which is half of 50 is 25, isn't it, students? So that's how is the calculation done. So what I want to say, that is the end of design of knuckle joint, but very important what I'm trying to say. If you have any doubt with respect to any equations, how we are going to do, always welcome to ask. Don't hesitate to ask. That is the beauty of design of knuckle joint. Just you should know. I wonder most of the students actually will fail very badly in a design. I wonder why. Because they give you a textbook, you have to just know where the formulas are located. If you have practiced well, it's not a subject to be found as tough. This is the most easiest subject. Okay, I myself have done MTech in machine design, and I just love this subject because it is with respect to have the set of formula book is given, either Balvi Reddy or the Mahadevan. So what I feel, Mysore students usually follow Balvi Reddy. It's good. I also followed. I studied in Vidya Vikas, so it's good to follow Balvi Reddy because it is very systematic. But when it comes to this one, Lingaya, I don't recommend. But in Bangalore, students actually under VTU will refer to the Lingaya. But you should be able to find the equation. I find it little complicated personally, I feel, because I felt it is easy because all the equations are readily available in the Balvi Reddy. But when it comes to Lingaya, you need a lot of practice, more practice. So Balvi Reddy is good. I recommend that. You always don't forget to hesitate to ask. Like the channel and subscribe and comment, and subscribe as usual, share to the maximum, and I'll also come up with a lot of many other videos which are very very important in design 1 and 2, and also other mechanical engineering subjects like dynamics also. But don't forget to subscribe to my channel and share to the maximum with your friends, and also don't forget to like and also comment. If you keep commenting, and what I feel motivated to do more so problems. So I'll also come up with all the designs of spar gear and other design aspects of DME2, and also with the dynamics also when it comes to governance and all. Okay, I'll always be there to help you. Don't forget to, last time I'll be telling, comment, share, like and subscribe to my channel. And also I'll be actually like I have my own blogspot also. Okay, the link will be given in the description, and you can also go through the various playlists in the description. And one more important thing is I also have Amazon products. So anything which is with respect to very interesting, you can always click on my link and go for subscribing to that. If you want to like that purchase, you can just directly purchase through my link, and it is the best funda of the thing is it is very good products I'll be promoting. And also with the Meesho app, do when you share, subscribe and comment and like, then only you'll come to know what I'm trying to say. So share to the maximum if you like, and also it is keep motivated. Thank you. See you then. Bye bye.